Hello again. We are almost done with this unit. There's two more topics. We have accuracy and precision, and we also have chemical and physical properties and changes. And then you'll be done with your very first unit in pre-AP chemistry. So this first topic that we have for today is accuracy versus precision. And when you're looking at your accuracy and your precision, you're actually going to look at first just the definitions of accuracy and precision and what that means for us in the lab. And then from there, you're going to look at some data sets with some math, and we will kind of figure out how to calculate, I guess, the accuracy versus your precision. So this first slide that you'll have when you're in your present mode, you should have downloaded this PowerPoint. Watch this video. Normally I give an analogy in class. Instead of recording that, I found just somebody else to talk at you in a video. So it's a pretty good analogy with your accuracy and precision. So then we have the actual definition of accuracy and precision. When we look at the definition of just accuracy first, we're looking at the target here, and it's how close you are to the accepted value. The accepted value is the one that everybody in the world says, hey, this is where you need to hit. So if you have a bow and arrow set with a target, you know that you're setting your sight on that middle of the target. Unless you're playing like a dart game, then you're going for a certain number, but we're not going there. We're just trying to hit the center of the target. So your accuracy is being able to hit your target. That is a little bit different than precision, which just means that you can get the same results over and over and over. So in science, when you're looking at your data itself, yes, you want to be right, but more importantly, you want to be able to replicate your results over and over and over. If you can replicate your results, you might be looking at something new in science itself. So being able to get the same results over and over is just as important as being correct. So on the target here, you have a little cluster of dots in that picture. You're not in the center of the target, but all of those are really close together. That's really good lab practice to be able to get the same results. So accuracy is getting the right answer. Precision is being able to replicate your results. So we have some data sets, and I'm going to switch over to my document camera here just so I can kind of write on them. You'll see something like this in a test or in a lab or things like that, where we're looking at the numbers that you get in the lab. There's no units with any of this, it's just numbers themselves. I want to kind of trim it down a little bit. But you have your accepted value up here. The accepted value is the correct answer. These are the data sets that you got in the lab. And we want to tell about the accuracy and the precision. And honestly, it's just they had good accuracy, they had not so good accuracy. They had good precision, they had not so good precision. So accuracy is getting close to the answer that you wanted. And when we look at this overall, these 5 data points, you're looking at collectively. So not like, oh, one is, no, just all together is the group close to the correct answer. And when we look at this, you should have 14.2, something very close to that. We're on all of these really close to 18, 17.9 to 18.4. That's a very close data range, but it's pretty far away from 14.2. So I'm going to say that my precision is not great. Nope. My accuracy is not great. Sorry. Wrote that in the wrong spot. So with my accuracy, I'm not close to the correct answer, so it's not very good accuracy. Now my precision, being able to get the same answer over and over and over, all of these numbers are very close to one another. So because all of those answers are very close to one another, I would say that my precision is pretty good. Again, it's overall, you're looking at the whole data set. Overall, my precision is good, but I didn't have good accuracy. Now, if I look at this next one, I should have 4.9. My data set over here, I'm anywhere from 15.2 to 14.7. Overall, those are pretty close to the 14.9. So I'm going to say that my accuracy is pretty good on this one. Ooh, sorry, it went blurry and I don't know why. Let me see if I can. Sorry, I don't know how long that was blurry. But my accuracy was pretty good because I overall had the correct answer. Now with my precision, they're all pretty much clustered in the same little area. So because they're all clustered in the same area, I pretty much replicated my results over and over. I'm going to say that my precision was pretty good. Now just as a general kind of tip here, if you have good accuracy, you're probably going to have pretty good precision as well, because your results aren't all over the place. Now on the last one, we should have 4.75. My answers here are everywhere. There isn't a whole lot of replication in those results. So right away that I know my precision is not good. They did not do that task very well, because they did the lab and they got 3.43. They did the lab again, they got 5.22. They did the lab again, 4.3. They're all over the place. So my precision is not good. Because my precision is not good, my accuracy, not good as well. You might be able to argue one of them. Actually, none of these you could even really argue. But let's just pretend like one of your data points is 4.74. You go, well, that one's really close, but all of those really stink. We're not really looking at one data point. Again, we're kind of looking at the numbers as a whole. And when you look at all of those numbers together, even like this, it's still not very good accuracy because they were only accurate one time out of those 6. So here, accuracy is not good, precision's not good. Now, going back to the notes, chemists don't like this because it's very subjective. It's looking at it going, well, maybe I could argue this, or maybe no. Chemists want like concrete answers, yes, no, good, bad, wrong, right, whatever. So what we actually have in chemistry is something called your percent error. Percent error is a mathematical calculation. And that mathematical calculation tells you exactly how much error there is in the lab itself. So you're going to have 2 different little data points here. You're going to have your accepted value and you're going to have your experimental value. You're going to subtract the difference between your experimental and your accepted answer. With the difference between them, it really doesn't matter how you subtract them because it's in those little lines, which means absolute 0, which means that you cannot have a negative for the top part of that. The negative magically disappears. I'm sure there's some math terminology for that. I'm just saying they're magically disappearing. So you're going to subtract the difference between your experimental and your accepted value. You're going to divide that by your accepted value. You're going to take that answer and multiply it by 100 because it's a percent, which means that your unit on this number is a percent. Your other units actually end up disappearing. They're actually canceling out as you go through that math problem, and that's going to leave you just with your percentage for your unit. So I'm going to write this equation down just so we have it, but your percent error is equal to your accepted value and your experimental value subtracted. You're going to do that first, and then you're going to divide that by your accepted value. That is a, I left not a whole lot of room. That is an absolute value, so you're going to get your answer there. So again, I'm going to go back to my practice problems. When I go back to my practice problems, sorry, I'm turning on the lights in the room again. They turned off on me. I think that's happened in every video so far. So I wrote down my equation up here just so we have it to reference. Again, your equations are going to be given to you. You don't have to memorize those. Writing an equation is not showing work. I want to know where are the numbers actually plugging in. So this problem says Dr. Gable was in the lab measuring the density of water. Hey, we already know the density of water, but I was measuring it. The answer that I got was 1.34 grams per centimeter cubed. The lab paper and our notes said that I should get 1 gram per centimeter cubed. I want to know, what is my percent error? So in order to do this, you're going to get the difference between your experimental, what you got in the experiment, versus your accepted value, which is the value that everybody in the world says that you should get. Experimental, what you got in the experiment. Accepted is what you should get if you were 100% correct. So with this one, we're going to take our experimental value and subtract off our accepted value. You're going to get a difference there for the number that goes on top up here. I don't need a calculator for this. If you need one, you can pick up a calculator, but I don't need one. It's 0.34. So then you're going to divide that by your accepted value. Your accepted value is the one that everybody in the world says that you should get. The accepted value for the density of water is 1 gram per centimeter cubed. So I have my 0.34 divided by 1. If this number on top happened to be negative, that would have disappeared, poof, vanish, because it is an absolute value. We're going to take our answer and multiply it by 100. So here we're taking 0.34 divided by 1 times 100. So that's 0.34 times 100. Hey, 34%. No calculator needed. So we got 34% error there. I got 34% error there. That is not a good answer. Just an FYI, you're aiming for 0 error. If you do the lab 100% perfectly, you're getting an answer of 0. In college level courses, if you got more than 15% error in my courses, we had to do the lab again or accept a 0, which is huge in a college level class where you don't have a bunch of daily points. When my upper level classes, we were aiming for 10% error. I will tell you, I don't grade your error. What I do grade is your reflection on why you have that error. So maybe I did this lab, and when I was measuring, my ruler had scratches in it and I couldn't measure correctly. I don't know. So when I get this answer, I say, oh, I got 34% error, but I think I know why. And then you'll be able to explain it from there. So when we're doing the labs in class, you'll be able to run this percent error equation, and then you'll be able to tell me why you have that error, because you'll actually do the lab itself. So in your mathematical calculations, you're going to do this in pretty much every lab as we go throughout the year, but we're looking for that accuracy in the lab, and then we're also aiming for precision. So as we look at these different math problems, you will look at your accepted and your experimental, and we will, like I said, do this in pretty much every lab as we go throughout the year.